I've got one more instructional video for you guys, and then we'll just start cranking out some problems because there's not really too much to energy. And we're going to talk about work a little bit more and one last new idea called power. To explain work a little more fully, I'm going to need some help. So I got my new friend Larry the Lifter, and he has a 50 kilogram dumbbell I guess, that he's carrying around, and we're going to calculate how much work he does as he moves this thing around. So here I've got a rough sketch of the building that Larry the Lifter works in, and he's just going to do a couple different things, and we're going to calculate how much energy it takes him to do it. So he's carrying a 50 kilogram dumbbell, and each floor is 3 meters high in this little building. So for the first question, how much work to carry it up 2 floors, let me just simulate his motion. So we've got Larry, he's chilling down here, and then he walks up the first set of stairs, and then he walks up the second set of stairs, and he's done. So at the beginning, he was at the bottom, and at the end, those 50 kilograms got 6 meters higher. So I would say the amount of work that was required for him to do that, since work equals force times distance, well, the force on those 50 kilograms was 500 newtons. So he lifted with 500 newtons of force over a distance of 6 meters, which would give me a work of 3,000 joules. By the way, don't be afraid of big numbers on this section because a joule is a very small amount of energy. You use a lot of them every day. So this answer shouldn't surprise you at all. Let's try another one. This one wants to know how much work it's going to take Larry to carry it 10 meters across the room on the bottom floor. So he starts out over here, and he simply holds it and walks across the room. You've had to carry stuff across a room before, right? And then he ends up there. And I want to know how much energy it took to do that to the object. So we do the exact same thing as before, right? Work equals force times distance. So he had a force of 500 newtons to lift the thing, and he carried it a distance of 10 meters. So we would say that it took him 5,000 joules of energy in order to do that. That was actually a trick. This answer is entirely wrong. The real answer is that the amount of work it took him to walk across the room with that was 0 joules. If you take a look at this 50 kilogram object that he's holding, the object didn't gain any energy. We've only talked about 3 types of energy so far, right? There's gravitational, elastic, and kinetic. Check it out. Over here, it pretty much started with 0 gravitational energy, and over there, it still had 0 gravitational energy. If you want to tell me that he gave some energy to it, you have to be able to tell me what kind of energy he gave to it. The answer here is 0. Let me try to explain why. Now, in order to make this point, I'm going to need a new friend, so I drew her for you. And it's Susie the Shopper. And she's not nearly as strong as Larry the Lifter, but she did something kind of clever. She put those 50 kilograms in a shopping cart. And now she does the same task that he just did. Even though he's very strong, all she has to do is just roll the thing across the room. And really, you could even have a small child, and as long as you give them a shopping cart, they're going to be fully capable of moving very large objects across a room. That's because you're not giving the object any new energy when you simply move it across a room. And here's the reason why. So instead of leaving you in the dark, let me just lay out a very simple rule for this. The formula that work is equal to force times distance is only valid when the force and the distance are in the same direction. In the example that I just gave you, they were pushing up on the object to hold it, but they were walking to the right. So that's why it didn't really take any energy as long as you had something to exert the upward force on it. But no energy was actually added to the object. In the other example, when he was actually lifting it up the building a little bit, well, he was giving it some energy because he was pushing it up and he was walking in an upward direction. So make sure whenever you use this formula that the force and the distance are parallel. They must be in the same direction. Now, if you understand the definition of work very well, then power shouldn't be that big of a big step for you. Power is simply how much work you do every second. It's how much energy you give to an object for every second that goes by. And there's a couple different formulas for it. You've got change in energy divided by time, or force times distance divided by time, because the change in energy is force times distance, or simply force times velocity, because if you want to take this distance divided by time, well, that's just velocity. So you could also write it in this form. But that's how you calculate power. And the units for power is called a watt, or we usually just write a small w for short.